Okay, we're going to try this again. Numbers 1 through 6 was on a separate video, and we're going to try and go from here. There are a bunch of problems, but none of my technology really seems to be working. So we have 26 total problems, and let's start with number 7. So 7 is an interesting question. It's talking about the Compton effect. So of course the Compton effect is when a photon collides with an electron and then transfers some energy and momentum to that electron. So it's and so it's like, well, if it's a collision, couldn't the kinematics equations be used? But the kinematics equations ignore the wave nature of a particle, or rather, it's just not really the wave nature, but the quantum energy of a particle, and the fact that the energy of the photon is hc over lambda, which does not lend itself to classical physics. And you can't just use the wave theory of light to explain Compton effect, because with wave theory of light there would be no collision between a photon and an electron, so it's not wave theory of light. The concept of the photon, which hc over lambda, that could be useful, except that the actual formula for Compton effect, where the difference in the wavelength of the photon is h divided by the mass of the electron it collided with times its speed times 1 minus cosine of the scattering angle, that h over mc, that's actually, they're pulling at h over mc, talking about the de Broglie wavelength of the electron itself. So it's not just the concept of the photon, it's a little bit of both. And so in the end, really the Compton effect, the change in the wavelength, is really just a question of conservation of momentum in the collision. So that is choice A. Number 8. X-rays of wavelength 100 picometers scattered from a block of carbon. So this looks like it's going to be some Compton scattering because it's light hitting electrons of carbon. Radiation is observed at right angles to the incident beam. And yes, indeed, it says what is the Compton shift for the observed radiation. Alright, so we have our original wavelength is 100 picometers and our angle is 90 degrees. And notice that it's not asking for the original, not asking for the new wavelength, it's asking for the shift, it's asking for the change in wavelength. So we have an equation for that. And it said the angle is 90, and of course the cosine of 90 is 0, so 1 minus 0 is 1. And so we get that the change in wavelength is simply Planck's constant over the mass of the electron times c, giving us 2.42 times 10 to the negative 12, or 2.43 I should say, which gives us B, 2.4322 picometers. Notice you didn't actually need the original wavelength to solve this problem. Number 9, light of intensity I and frequency f above the threshold frequency is directed at a polished metal surface. Okay, so threshold frequency, what does that mean? So that threshold frequency is the frequency of the light that would overcome the work function and get electrons to come off of the photosensitive surface for photoelectric effect. It says 3 claims are made about electrons ejected from the surface. So this one's kind of weird, and it says, all right, so things that are true. The ejection is instantaneous. The number a number of electrons ejected is proportional to the intensity, and the kinetic energy is equal to Planck's constant multiplied times F. And so the third statement is incorrect, because we know that the kinetic energy is is hf minus the work function. It's not just simply Planck's constant multiplied times F, so it can't be 3. And so B has 3 in it, C has 3 in it, D has 3 in it. That leaves only A. Now it's like, what's the deal? Like, ejection of the electron is almost instantaneous. Okay, but the number ejected is proportional to the intensity. The intensity had no effect on the electrons. It's talking about the number ejected. It's not talking about their energy. The energy is not related to I. But if you can imagine that electrons are being emitted because of the impact of photons. So a greater intensity, more current means more photons means more electrons. So that would actually potentially show a greater current in terms of the photoelectric current, but the energy would not be related to the intensity. So you could have a brighter light, and the brighter light is not going to change the stopping voltage, which we now know is proportional to the energy by E equals QV, right? So a greater intensity won't change the energy or the stopping voltage, but it might lead to, well, it would lead to more electrons being emitted, so a greater current. And again, the way these pages are breaking, I have to go all the way back over here, but it does say that yes, A is the correct way to go. All right, here we have number 10. Interesting, number 10 is a very interesting question. Now let's keep in mind, we're talking about the current I, so the current for this question, the current is the number of the electrons, it is not the energy, right? So that we know the energy is proportional to the frequency, so as frequency goes up, energy goes up, but not the number of electrons. And it says that the number of photons incident per second, that's the intensity of the light, that is constant. If the intensity is constant, then the number of electrons that will be emitted is also constant. But note the threshold frequency. If you don't hit that threshold frequency, you're not getting anything, right? You have to overcome the work function first. So before you hit that threshold frequency, you have nothing. And then once you hit the threshold frequency, immediately you start getting a current. But if your intensity is constant, then your current is also going to be constant. And so graph A is the way to go. Again, we're talking about current here, not energy. If it was energy, it'd be B. Number 11. Light falls on a metallic surface. Threshold frequency is F naught. Number of photons incident is constant, which shows current. Wait a minute. It's the exact same stupid question. Ugh. Okay, so then let's look at number 12. Light frequency F, incident metallic surface with a work function W, photoelectrons with kinetic energy max are emitted. Frequency of the incident light is doubled. What is true about the kinetic energy and the work function? So the work function is a property of the metal. It's not a question of the light that's on the metal. So the work function is going to be unchanged. So it is not B and it is not D. And then if you increase the frequency, you're going to have a greater maximum kinetic energy. So as frequency goes up, the energy goes up. So the maximum kinetic energy is going to be greater, and the work function is unchanged, which agrees with the Mark scheme. I don't understand why it's greater than double. I would think that if you double the frequency, it's double the energy. So I don't know why it's greater than double. But I mean, it's certainly not less. So if you increase the frequency, it's going to have more energy. So by process of elimination, it has to be C. But I'm not why. I would say that it's double, not greater than double. I'm not sure where they're getting with that. But yeah, it's clearly answer is clearly choice C, because it can't be the other guys. All right, 13. So this one's interesting. And it may actually explain why 12 is greater than double, because it has to do with the work function. But anyway, so 13 says monochromatic electromagnetic radiation ejects photoelectrons from metal surface. Minimum frequency for which this is possible is F. So basically, like the very smallest amount is F, which means that kind of like that's the kinetic energy is zero, just barely happening, just getting over the work function, which means if the kinetic energy is just starting, is zero, that means that with HF minus the work function, the work function is going to be HF. So if EK is zero, you have that EK is HF minus the work function, and if EK is zero, then the work function has to equal HF, right? So to subtract out to zero. So if the work function is HF, it says when the frequency is 2F, so instead of HF I put in the 2 there, this guy here, right? 2HF minus the work function, and the work function is HF, then 2HF minus HF is just simply HF. And so when the frequency HF, when the frequency is 2F, and I was like, well, what about when the frequency is 4F? So instead of 2, I put in 4, but the work function is still HF. So I have 4HF minus the work function gets me 3HF. And so when the frequency is 2F, the kinetic energy is simply HF. But when the frequency is 4HF, I get 3HF. So it's 3 times as much. So that'd be 3K, and that's choice C. Maybe I'll divide this into 3 videos. The first one was through 6 because my iPad was acting up. But maybe I can get through 18 and we'll do 3 videos of this. Anyway, so 14. We have a photoelectric effect setup. And it says the work function for the metal is 12.8 times 10 to the negative 20 joules. What's the minimum voltage required to kill the ammeter? All right. Oh, and it says light with photons of energy 8 times 10 to the negative 20 are incident on the metal surface. So let's zoom 8 times 10 to the negative 20. Let's write that here. 8 times 10 to the negative 20 joules for the light. Okay, cool. And it says the work function is 4.8 times 10 to the negative 20 joules. All right, minimum voltage to get the ammeter reading to fall to 0. So what is that? Getting the ammeter to fall to 0, that's stopping the electrons from crossing the gap. And so really what they're talking, the minimum voltage to get that to happen, what are they talking about? The stopping voltage. All right, so basically I want to just barely stop the electrons from getting across. And so the light's coming in with 8 times 10 to the negative 20 joules. And at baseline, that light has to overcome the work function to get the electrons off the plate. And that work function is 4.8 times 10 to the negative 20 joules. So that means the electrons are crossing the gap with 3.2 times 10 to the negative 20 joules. Now I want to stop those electrons. So in order to stop them, I have to have an electrical energy, a QV across the plates there to kill that energy. So I need a QV that is equal to that 3.2 times 10 to the negative 20 joules. And so when you do 3.2 E10 times 10 to the negative 20 divided by 1.6 times 10 to the negative 19, we get 0.2 volts. That is A. Okay, number 15. What is evidence for wave-particle duality? Line spectra of elements. Line spectra is a pretty cool discovery showing quantization of energy. It does not show wave-particle duality, so it is not A. Rutherford alpha scattering is also pretty cool, but that is particles hitting particles, so that is not a wave-particle duality thing. Gamma ray spectra, I'm not even really sure what they're talking about. I think that's similar to A, with line spectra of elements or something. I mean, I think it's pretty obviously B. Electron diffraction. Electron is a particle. Particles don't diffract. That is a wave phenomenon. But particles do diffract because of wave-particle duality. The electrons have both wave properties and particle properties, as do photons. And so 15 is B. All right, 16. Very similar to number 15. Wave-like properties of electrons. Can electrons be used to investigate the structure of crystals? Yes, by electron diffraction. So yes, anything that has 1 in it. So it is not C. Okay, statement 2. Electron beam produces a pattern of fringes when sent through 2 narrow parallel slits for the same reason. Yes, electron diffraction. So statement 2 is correct. But then 3, electromagnetic radiation ejects electrons from the surface of a metal. And then it says, which is true. That's the photoelectric effect, that's true. But it says, which statements are explained using the wave-like properties of electrons? The photoelectric effect has to do with the particle properties of photons. not the wave-like properties of electrons. So even though statement 3 is true, it does not require wave-like behavior of electrons. So not 3. So no, no, and 1 and 2 only, because 1 and 2 pretty much explain the same thing, being electron diffraction. Okay, 2 more problems in this video. We have number 17. Dashed line represents variation with incident electromagnetic radiation. Incident electromagnetic frequency of the kinetic energy of the photoelectrons ejected from a surface. It's then replaced with one that requires less energy to remove an electron. What is the variation of kinetic energy with frequency? And of course the page breaks badly, so we have to go look at the graphs all the way over here. Ooh, that's messy. AB, oh, the dashed line is what it was originally, right? These page breaks kill me. Dashed line is what it is originally, then it's replaced with one that requires less energy to remove an electron from the surface. So in other words, smaller work function. Smaller work function. Okay, and so let's go look at the graphs. And so we know, and so just to explain what the work function is on this graph, it's if you actually extrapolated that dashed line down into kind of like the negative energy, that where the y-intercept is on that graph, that's actually the work function that needs to be overcome first. So it's a smaller work function, meaning that the y-intercept is going to be higher, like it's going to be a smaller gap from 0. And so it's not even that the slope is not going to be any different. If there were a steeper slope, there'd be a higher frequency. That would be B. But it's the same frequency, so it's not B. And a smaller frequency would be C. And a bigger work function would be D, because D is going to intercept all the way down there. So we're left with A. A smaller work function, A is going to intercept right around there. So that's going to be the work function for A, so A is our graph. And then the last question for this video, I'm glad that explained everything, is behaving itself, knock on wood. But anyway, 18, photoelectric experiment, stopping voltage V required to prevent photoelectric electrons from flowing across the cell is measured for light of 2 frequencies, 1 and 2, and the results are shown. Okay, yes, for a higher frequency, that would be a higher energy, so it would be a higher stopping voltage, true. And, ooh, we already answered this question. So it says, what is the ratio of the difference in the voltages divided by the difference in the frequencies? And we already said that was H over E, but the logic, I think that was in the first video, actually. Let me see if I can find the question. That was number 2. H over E. Yeah. So on the reasoning on that, C number 2 in first video of 3. I hope there's only 3. But yeah, it's going to be H over E. That's kind of annoying, right? Am I really going to make you go look up the other video? All right, let me re-explain it in this video. Okay, so EK, HF minus the work function. So kinetic energy is QV, which is HF minus the work function. And so the stopping voltage is just at the point where you just overcome the work function, the minimum, let's see. The minimum stopping voltage. And for the 2 different frequencies, we have QV equals HF. And so the voltage winds up being HF over Q. And the frequencies cancel, so we wind up with H over Q or H over E. How do they phrase it in this guy? H over E, because E is the electron. H over E. And that is choice D. Okay, so that's about 20 minutes. That's 18 problems between the two videos, and then 19 through 26 will be in another solution video. Thank you.